Lesson 12.5 Integrals. So integrals deal with summations. And so here are some summation formulas that will come in handy. If you add up a constant from 1 through n, so it's like c plus c plus c plus c plus c n times, you just have c n times, or c times n. If you're adding up I, this would be like 1 plus 2 plus 3 plus 4 plus through n. You get that. This is squared, so 1 squared plus 2 squared. And cubed, which would be 1 cubed, 2 cubed, and so on. Well, these sums have properties. It's adding, so it has all the properties of addition. Has the associative property, which means we can group it differently. We can either add the numbers together first and then do the sum, or do the sum of each function separately and then add them together. We also have the distributive property. If you're multiplying the function by a number, k, it's the same thing as doing the sum of the function first and then multiplying by k afterwards. It's just distributing because every term would have k. Let's find the limit of this sum as n approaches infinity. So in other words, I've rewritten it, the limit as n approaches infinity of the sum from I equals 1 through n of I minus 5 over n squared. Well, there's a couple ways we could go about doing this. One way is we could split our fraction here into two parts. I over n squared minus 5 over n squared. And then we could use the associative property and do the sum of each one of those. Now, the variable of summation is the I. So anything that's not an I could be factored out of each of the sums. So I could factor out a 1 over n squared from the first sum, leaving the sum of I. And the second sum doesn't even have an I. So it's like the sum of c. So this one we have a formula for. So it's 1 over n squared. And then its formula is n squared plus n over 2n squared. And then we have a formula when there is no I, when it's just a c, it's that times n. All right. Oops. Sorry, there's no n squared there. So now we could simplify each of those. Here's where I had my n squared. So just multiply the 1. All right, and then property of limit says I can do the limit of each one. So I could do the limit of the first one minus the limit of the second one. And yeah, I know I could reduce the fractions. But the first one, the degrees are the same, so what's the leading coefficient? So that's 1/2. And the second one here is the case where n is less than d, so the limit is 0. So our limit is 1/2. The second problem in calculus that they focus on is the area problem. So finding areas using functions. So we're going to find the area between a graph and the x-axis, between two x values a and b. So here's our a, here's our b. So imagine drawing a bunch of rectangles with the top corner on the graph. The areas would approximately be the area of the rectangles. Now that'll be an overestimate, of course. But if I put in more rectangles so that they were skinnier, it would be a closer. So let's say I put in twice as many. That little bit wouldn't be there anymore. And so it would be a better estimate. So we would like the more rectangles. We'd like an infinite number of rectangles. Well, our area of each rectangle is the length times the width. And if I add those all together, so I have a sum. Well, the length of the rectangle, let's call that the height. All right, so what will it be? It will be an A, but then I need to add the width. The width is going to be b minus a divided by the number of rectangles. So if we're going through 8, it's from 0 to 8, and we want 12 rectangles, it'd be 8 over 12 for the size, the width of each rectangle. So we have our a plus our width. But if I want this last one down here, I'm going to have the width times the number of rectangles that we've already done. So we have our a, our width, times the number of rectangles we've already done. And shortcut way of writing it is the integral from a to b of f of x with respect to dx, or with respect to x, so dx. F of x dx, that tells us what variable we're plugging the a and b into. So this is called an integral. Let's find the area bounded by f of x equals 2x squared, and x equals 0, and x equals 1. So this is the same thing as the integral from 0 to 1 of my function, which is 2x squared dx. That is going to equal the limit as n approaches infinity of the sum of f of a plus b minus a over ni times b minus a over n. Let's work out each part of this nice complicated limit. All right, let's start by filling in our a and b. Our a is 1, our 0, our b is 1. So the a is 0, b is 1, a is 0. b is 1, a is 0. Yes, you need to write all the symbols. All right, so this become f of 1 over n I times 1 over n. Okay, next we could take care of our function. So f of 1 over ni, my function is there, is 2x, but x is 1 over ni squared. Okay, we could multiply things out. So I square 1, it's just 1. So this becomes 2 over n squared, I squared. The I and the n become squared. And that is times by 1 over n. So then that becomes 2 over n cubed I squared. All right, now let's work on our sum. For the sum, we could factor out everything that's not an I. So I could factor out the 2 over n cubed. All right, but we have a formula for I squared. So let's use that formula. That was 2n cubed plus 3n squared plus n over 6. Could distribute. So that would be 4n cubed plus 6n squared plus 2n over 6n cubed. And now we can take our limit. The degrees are the same, so it's the leading coefficients. So it's 4 over 6, or 2/3. So the shaded area in the little graph up here is 2/3 of a square. Let's find the area between this nice parabola and the x-axis, between 1 and 3. So in other words, I want the shaded area in this graph. So that is the same as an integral from 1 to 3 of my function with respect to x. But that's going to equal the limit as n approaches infinity of our sum of f of a plus b minus a over ni times b minus a over n. We could start by filling in the a and the b. A is 1, B is 3, A is 1, B is 3. Okay, this become f of 1 plus 2 over ni times 2 over n. Okay, we could plug in our function next. So it's 4 times x, but my x is 1 plus 2 over ni, minus x, which is 1 plus 2 over ni squared. So all of that is my function times 2 over n. We could distribute the first part, so that'd be 4 plus 8 over ni, and our binomial theorem for the second part will be 1 squared plus 2 times 1 times 2 over ni plus the 2 over ni squared I seem to be writing uphill. Sorry about that. All right, let's collect like terms. So I have a 4 minus 1. For i's, I have 8 over n plus 4 over n would be these should be minuses, sorry, because there's a minus there. 8 over n minus 4 over n would be 4 over ni, and then a minus 4 over n squared, I squared. All right, we can distribute. So that would give me 6 over n plus 8 over n squared I minus 8 over n cubed I squared. Okay, I could apply the associative property and write these as separate sums. And then could factor out anything that's not an I. If I factor out 6 over n and that's all that's there, it's just a 1. Next one, I can factor out the 8n squared, leaving I. Then the next one, I can factor out the 8 over n cubed, leaving I squared. I'm running out of space, so we're going to continue this on the next slide. So this is where we were. Now we have formulas we can apply. So we have a formula for that. So 6 over n times, and it's just a constant, so it'll be 1 times n. Then we have 8 over n squared, and we have a formula for I, which is n squared plus n over 2. And then we have a formula for the I squared, which is 2n cubed plus 3n squared plus n over 6. Could simplify each of those. So it'll be 6. This will be 8n squared plus 8n over 2n squared. And then we'd have 16n cubed plus 24n squared plus 8n over 6n cubed. And then technically we have separate this into separate limits, so let's go ahead and write that out. So it'll be 6. And the limit of the next part minus the limit of the last one We evaluate each of them. Limit of a constant is the constant, so we have 6. Degrees are the same, so it's leading coefficients. 8 over 2 is 4. And then we have, again, leading coefficients, 16 over 6. We can reduce those by 2, be 8/3. So we have 10 minus 8/3. Need a common denominator, so it'll be 30/3 minus 8/3, which is 22/3. And that is the amount of area in that little graph that we had.